My name is Alexandra Jabouri, and the purpose of my video today is to teach a grade 12 advanced functions concept. So, let's look at the question. For what values of n will the reflection in the function y equals x to the exponent n in the x-axis be the same as its reflection in the y-axis? For what values of n will the reflections be different? Explain your reasoning. Okay, so let's look at the key elements of this question. Okay, we're going to be looking at the function y equals x to the exponent n, which is a power function. Okay, we're looking for different values of n and whether the reflections in the x and y axis are the same or different. Alright, so let me just explain power functions. So when there's an exponent, it's a power function. There's odd degree and there's even degrees. So an odd degree power function is when n is an odd number, as we see here. And even degree power functions is when n is an even number. Alright, so here's the plan to solve this question. We're going to compare the graphs of the function y equals x to the exponent n and see if the reflections in the x and y axis are the same or different, while also looking for patterns within the values of n. Okay, another way we're going to solve this is algebraically, using the Unit 1 concept of even and odd symmetry. So, looking at the questions again, for what values of n will the reflection of the function y equals x to the exponent n in the x-axis be the same as its reflection in the y-axis? Explain your reasoning. Second part, for what values of n will the reflections be different? Explain your reasoning. Okay, so quickly I'm going to explain the concept of even and odd symmetry. Basically, with even symmetry, the function is symmetric about the y-axis. Algebraically, it looks like f of negative x equals f of x. A function that has odd symmetry is a function that has rotational symmetry about the origin, right? Here's the origin. And algebraically, that looks like f of negative x is equal to negative f of x.
Okay, so let's start by plugging in some odd integers and looking at their graph. Okay, so let's look at only y equals x to the power of 3. Let's look at it when it's reflected in the y-axis. Okay, so looking at the function y equals x to the power of 3, which is the basic function, this is the red graph, okay? When we reflect it in the x-axis, it's going to be y equals negative x to the power of 3, which we see here is the blue graph. When we reflect it in the y-axis, it's going to look like this. Y equals bracket negative x bracket to the power of 3, and this is the green graph. So let's look at the blue, at the green. These graphs seem to be the same. Let this not be our only example. Let's look at y equals x to the power of 5. So looking at the orange graph, that is the reflection in the x-axis, and looking at the reflection in the y-axis, the purple function here, looks like they're both the same. So yeah, we just gotta see algebraically if this is true.
Okay, so we know graphically that the functions y equals x to the power of 3 and y equals x to the power of 5 have the same x and y axis reflections. Okay, this means that they must have rotational symmetry, okay, or odd symmetry. And algebraically, we're going to prove this by using this equation, f of negative x equals negative f of x, okay? So let's start with f of x equals x to the power of 3. We see the equation here, okay, this is in an expanded form. And we see down here that this is equal to this, right? So therefore we can conclude that f of negative x is equal to negative f of x, meaning that there is rotational symmetry. Okay, let's look at it for x to the power of 5. Right, here we have the equation. This is an expanded form. We can conclude that f of negative x equals negative f of x. Okay, so let's look at the pattern here. They're both for both graphs, n is an odd integer, so we can conclude that for the graph y equals x to the exponent n, the x and y axis reflections will be the same for odd values of n.
Alright, now let's plug in some even integers to see if the x and y axes reflections will be the same or different. Let's look at the function y equals x to the power of 2, and another even function would be y equals x to the power of 4. Alright, so let's look at y equals x to the power of 2. Here, looking at the orange graph, that this is the reflection in the x-axis, and this is the reflection in the y-axis. So yeah, they're different. Okay, let's get another example. Y equals x to the power of 4. Okay, so let's look at this black graph here. The reflection in the x-axis looks very different from this red graph here, which is the reflection in the y-axis. So let's prove this algebraically.
Okay, so we saw graphically that the functions y equals x to the power of 2 and y equals x to the power of 4 have different x and y axis reflections. Okay, this means that they must be have even symmetry, because functions that have even symmetry only have symmetry about the y-axis. Okay, algebraically that looks like f of negative x is equal to f of x. Okay, so let's prove this. Looking at the function f of x equals x to the power of 2. Okay, here's our equation for even symmetry. There, negative x to the power of 2, expanded form. Alright, therefore we can conclude that f of negative x is equal to f of x, therefore it has even symmetry. Okay, let's look at x to the power of 4. We see that there's the equation for even symmetry, negative x to the power of 4 in expanded form, and x to the power of 4, therefore f of negative x equals f of x. So looking at this pattern, okay, we see that both values of n are even, therefore we can conclude that for y equals x to the exponent n, the x and y axis reflections will be different for each value, even value of n. Okay, so our full solution, right, for this whole question is for y equals x to the power of n, the x and y axis reflections will be the same for odd values of n. For the same graph, the x and y axis reflections will be different for even values of n. Okay, and we solve this algebraically and graphically. Woohoo! So a career where you would solve this type of problem would be a statistician. Basically, statisticians collect information from surveys and experiments. They decide where and how to gather the information, who to survey, and what questions to ask. They use this information they collect to make predictions about the economy or to assess various social problems. This helps the business and the government leaders make decisions. Statisticians make about 50 grand or more per year. They need to know a lot of calculus and different math topics. There's actually 71 different math topics that statisticians need to know. Some of those include metric measurement, basic problem solving, linear equations, quadratic equations, algebraic representation, operations with polynomials, rational expressions, coordinate graphing, logarithms, and yeah, a lot of stuff we learn in grade 12. And they may not solve a problem exactly like this, but their career definitely revolves around a lot of graphing.